All right, let's dive right in. Welcome to channel YouTube Indra Ramat for this explainer. Today, we are putting a massive industry claim right under the microscope. We're going to test whether the enormous hype behind the new Ling 3.0 Flash Agentic model actually holds up when the rubber hits the road. Now, there is a ton of buzz surrounding this release, right? It's built specifically for production scale, agentic inference, and it promises to be fast, cheap, and super smart. But as anyone who writes code knows, how an AI performs on a sterile, controlled test is often very, very different from how it survives in the trenches. And that brings us to the core theme of our explainer today: expectations versus reality. If you've spent any time looking at AI demos recently, you've seen the glossy, flawless videos. You know the exact ones I'm talking about, where a user types a single sentence, walks away to grab a coffee, and the next morning, their AI agent has perfectly built a full app and supposedly earned them $10,000. Well, as we quickly find out when digging into the data, that just doesn't happen in the real world. The actual reality of debugging AI agents is frustrating, it's messy, and it usually involves a whole lot of manual handholding. So we're going to strip away the viral magic and look at what actually happens when you push a modern model to do real gritty work. Now, look at the staggering headline claim being made by the developers here. We are looking at a true David versus Goliath situation. Ling 3.0 Flash is a mixture of experts model packing 124 billion total parameters. But, and here's the kicker, only 5.1 billion parameters actually fire per token. The developers claim that this highly efficient, smaller model matches the performance of those massive 1 trillion parameter flagship models across major benchmarks. To put that into perspective, it's supposedly achieving top-tier reasoning and coding capabilities using only 1/8 the total parameters and an astonishingly low 1/12 of the active parameters of its giant competitors. That's a huge claim. So how does it theoretically pull this off? Let's break down this brilliantly engineered hybrid architecture. Think of it like a highly organized corporate office. Down in the lower layers, you have Kim Delta Attention. This is a linear complexity mechanism. So it basically acts like an incredibly efficient mailroom that scales perfectly with massive documents. It means it processes long contexts super cheaply. Then in the middle, you have your specialized departments. Mixture of expert blocks featuring 512 distinct experts plus 1 shared expert. But crucially, only 8 of them are active at any one time to save energy. Finally, up top, the upper layers use gated multi-head latent attention. Think of this as a ruthless executive team compressing the key value cache, keeping the memory footprint incredibly low at serving time. On paper, absolute masterpiece of efficiency. Okay, enough about the theoretical specs. Let's pivot to our first real-world test. We are completely bypassing the standard artificial benchmarks for this. Instead, Ling 3.0 Flash is being hooked up via the Hermes agent and tasked with fixing a totally broken codebase for a report generator. There are no hints, no detailed roadmaps. The AI is simply dropped into the environment and told, find and fix every bug. To really grasp what the AI is up against, we need to quickly look at the environment it's trying to fix. Here is the exact 4-step asynchronous pipeline. First, a user asks for a sales or inventory report, and the API backend receives that request. Simple enough. Second, the backend publishes that job to Redis. Third, a worker process is supposed to pick that job up from Redis and process it. And step 4, it writes the completed result back into an SQLite database so the front end can display it. It's a very standard real-world architecture. So what exactly did we break? Well, we didn't just make a single typo. We planted 4 specific, nasty bugs scattered across 3 different files to really dial up the pressure. First up, the front end completely fails to communicate with the back end. Second, the submit route stubbornly rejects all post requests. Third, even if a request somehow gets through, the worker process is listening on entirely the wrong Redis channel, so it never even sees the job. And fourth, if it magically got the job, it's programmed to write the results the completely wrong database column in SQLite, meaning the status will never, ever update to done. We're talking about a complex, multi-layered mess. So we unleash the Hermes agent powered by Ling 3.0 Flash, and we wait. And any developer watching this is going to deeply empathize with what happens next. After over 10 minutes of staring at the screen, watching the agent try to use tools, backtrack, check files, it completely jams up. The agent gets stuck in an infinite loop. It spends all its time furiously trying to start up the backend and front-end services, but it continuously fails. Why? Because it hasn't figured out that it needs to activate the virtual environments first. It is literally spinning its wheels, totally paralyzed by basic environment setup. Actually, scratch that. It gets worse. Let's look at what happened when we manually interrupted the loop and gave it a little nudge. The agent finally found a bug, but then it entirely confused itself. It looked at the code, saw a GET request, but elicited that it had already successfully changed it to a POST request. It started going in circles, reading the same file over and over and over, eventually triggering rate limits on the API. Ultimately, after all that time and effort, the agent completely failed to independently find and fix the core issues. It required constant handholding, which pretty clearly proves that autonomous debugging is still incredibly brittle. Okay, so it struck out hard on debugging a local environment. Let's transition to our second test. We are moving entirely away from fixing broken code. Instead, we're going to test pure, from-scratch creative code generation. We want to see if this model can build something complex and visual with zero frameworks to lean on. But before I drop this prompt on you, we need a quick culinary detour to set the scene. Our subject for the simulation is currywurst. For those who haven't had the pleasure, this is Berlin's absolute most iconic street food, invented way back in 1949. It is so beloved it literally has its own museum, and over 70 million servings are consumed every single year in Berlin alone. It's legendary. And it is going to be the star of our physics simulation. Now, get a load of the sheer audacity of the prompt we gave Ling 3.0 Flash. We asked it to create a real-time currywurst cooking simulation using a single prompt. The catch? It has to be pure HTML canvas. No external libraries, no physics frameworks, no APIs. Just the model's raw ability to think in pixels and math. We asked it to simulate the cooking progression over a fire, render fluid dynamics for the sauce, create wet reflections, and generate realistic rising smoke. We are essentially asking an AI to build a custom 2D rendering and physics engine from absolute scratch in one go. Surprisingly, the model actually spits out the code remarkably fast. But when we save it and open it in the browser, oh boy, it looks terrible. It looks exactly like a primitive 2005-era Flash game. Now, to be fair to the model, the cooking gradient, the way the sausage changes color over time, that looks okay. And the rising smoke effect is there, even if it's a bit clunky. But the physics, the fluid dynamics, and those wet reflections we asked for, total fail. They failed completely. It's just a messy, primitive attempt that falls way, way short of the complex simulation we requested. Which brings us to the end of our explainer, and honestly, to a massive, messy reality check. Look, Ling 3.0 Flash has a brilliant architecture, absolutely, and on paper, it legitimately competes with models 10 times its size. But when we actually put it to work, it got trapped in virtual environment loops and completely failed to render basic physics. So I want to leave you with this provocative question to ponder. If our most advanced AI models can absolutely ace the hardest theoretical benchmarks, but immediately trip over themselves trying to fix a basic local database pipeline or simulate simple physics, are we actually measuring artificial intelligence, or have we just built incredibly good test takers? Thanks so much for joining me on this explainer, and I highly encourage you to keep questioning that gap between the slick demos and the reality. See you next time.